Okay? So next we'll show that the set of rational numbers is countable. And we'll state it as a lemma. Okay, so we will define a function f, mapping a product of the integers with the positive integers into the set of rational numbers, and we'll define this by f of mn. So we have as an argument an ordered pair where the first integer, or the first element, m, comes from the entire set of integers, and the second element, n, comes from the set of positive integers. And we'll define this function by m, the ratio of m to n. And as the second element, n, is from the set of positive integers, it is never 0. Now, remember, every rational number can be expressed as a ratio of integers, but that ratio, or that representation as a ratio of integers, need not be unique. But if we let the number q be a rational number, then this number q is represented by integers m to n, where the integer n is not 0, and this is true for some element m, which is any integer, and the element n, which is a positive integer. And so for every rational number q, there exists at least one ordered pair mn in the product of integers with positive integers, such that the function f maps that ordered pair onto the number q, which is our rational number. And so we have demonstrated that the function f, mapping the product of the integers with the positive integers onto the set of rational numbers, is surjective. Now, the product of the integers with the set of positive integers is a finite product of two countable sets. It is a finite product of countable sets. It is countable. And so, as it is countable, there exists a surjection, which we'll call G, mapping the positive integers onto this product. And so the composition of f with g is a map from the positive integers into the set of rational numbers. And since both the functions f and g are surjective, the composition is surjective. And so there exists a surjection mapping the set of positive integers into the set of rational numbers. And so the set of rational numbers is countable. Now further, as this set of rational numbers is an infinite set, that is, it is not finite, and since it is countable, it must be countably infinite. Okay? Now, as a subset, Well, first we'll define real numbers, I suppose. The real numbers which we denote with a script or blackboard bold letter R, consists of all decimal numbers. So as a subset of the real numbers, the rational numbers consists of either terminating or infinitely repeating decimals. So we'll look at an example of each. For example, the number 0.25 is what we call a terminating decimal. But what do we actually mean by terminating? The word terminating does not really imply that it ends here, rather that every digit past a certain point is the digit 0. So it is an infinitely expanding decimal, as it must be, as it is a real number. But we call it a terminating decimal because every digit past a certain point is the digit 0. And so the part that we're actually interested in are those digits that do not have the digit 0 after a certain point, or are not all zeros after a certain point. And so as we know, the number 0.25, if we read it off, is 25/100ths. So there's one ratio of integers, but we can simplify this to be 1 to 4. Ratio of 1 to 4, and so a terminating decimal is a rational number. Now the other example is an infinitely repeating decimal. So for instance, take the number 0.111 that repeats off into infinity. That is the digit 1 repeating indefinitely. To show that this is a rational number, let the number x be equal to 0.111 and so on. Then, if we multiply by 10 on both sides, 10 times x, we'll move the decimal place once, and so we have 1.111 and so on that continues off to infinity. If we now subtract the first from the second, we have that 9x is equal to 1, and so x is the ratio of 1 to 9. And so, again, as a subset of the real numbers, the rational numbers are those decimals that either terminate or repeat indefinitely. So next we'll define the irrational numbers. The irrational numbers are infinite decimal expansions that do not repeat. And so they cannot be represented as a ratio of integers. The symbol for the irrational numbers is the set of real numbers, set minus the set of rational numbers, that is the complement of the rational numbers in the set of reals. So in other words, if we take the entire set of real numbers and we eliminate all the rational numbers, that are the numbers that can be expressed as ratios of integers, then we are left with the irrational numbers. Okay, so next we'll show that the real numbers as a set is uncountable. And the proof that we're going to use is known as Cantor's diagonal argument. Georg Cantor first proved that the real numbers were uncountable in the decade of the 1840s, but he later came up with what we are now going to use, again known as Cantor's diagonal argument, which to me is much more elegant as it is a very simple idea. And that idea is that if a set contains, as a subset, an uncountable set, then the larger set itself must be uncountable. First we're going to assume that a subset of the real numbers is uncountable, or rather is countable, and then show by contradiction that it is uncountable. And then as it is a subset of the real numbers, the entire set of real numbers must be uncountable. So let the open interval I be the open interval from 0 to 1. That is, all decimal numbers from 0 to 1, but not including 0 or 1. And we're going to suppose that this interval is countable. So again, by definition of countable, it has to be in a one-to-one correspondence with the set of positive integers. That is, we can form a sequence with the elements in the open interval. So the open interval I can be expressed as a countable sequence, x sub 1, x sub 2, x sub 3, and so on. We use shorthand, x sub n, such that n is a positive integer, so a countable sequence. So we begin by constructing such a sequence. So for instance, the first element in the sequence is the number 0.A11, A12, A13, and so on. The second element is the number 0.A21, A22, A23, and so on. The third element is the number 0.A31, A32, A33, and so on. So that in general, the nth number in the sequence is the number 0.A in 1, A in 2, A in 3, and so on, to A in n, and so on, where each of the digits, A sub ij, is a digit from 0 to 9. So true decimal expansions, infinite decimal expansions between the numbers 0 and 1. So to show that this sequence of numbers is not countable, we are going to construct a number which is in the open interval from 0 to 1, but which is different from any of the numbers in the countable sequence. So we construct this real number, which we'll call R, and this is the number 0.B1, B2, B3, so on, to Bn, and so on, where B sub n is the number 2 if A sub nn is not equal to 2, and is the number 3 if A sub nn is equal to 2. So notice that what we're doing here is saying that given the assumption that the open interval from 0 to 1 is countable, then it can be expressed as a sequence, a countable sequence of numbers. And looking at the diagonal elements, A sub 1, 1, A sub 2, 2, A sub 3, 3, and so on to A sub nn, we're going to construct a number R, which is certainly a number that is in the open interval from 0 to 1, But each of the numbers, each of the digits in the decimal expansion is different from any that we have in the countable sequence. Because if, for instance, a sub 1, 1 is the digit 2, then we're going to make it the digit 3. And then if it is not the digit 2, we're going to make it the digit 2. So in other words, this real number r, which is in the open interval from 0 to 1, is different from any that exists in the countable sequence. It will differ in the nth decimal place for any of the numbers that appear in the countable sequence. So since we have this real number r, which is in the open interval from 0 to 1, but this number is not in the countable sequence, and again, this is since the real number r differs from any of the numbers in the sequence x sub n in the nth decimal place. We have by contradiction the open interval from 0 to 1 is not countable. And since this interval is a subset, a proper subset of the real numbers contain an uncountable set, an uncountable subset, and so the real numbers, the entire set of real numbers, is also uncountable. Now this is the first set that we've looked at, or that we've proven is uncountable, and so we need to talk about its cardinality. Now remember, the cardinality of a countable set is the transfinite number aleph null. For an uncountable set, we have a new transfinite number, and that is the number c, where the number c is a reference to a continuum. And so what we mean by a continuum is, given any two real numbers, each of the gaps between those two numbers is completely filled by elements in the set. So in contrast, for instance, a countable set such as the set of rational numbers is not a continuum, but is rather, they exist in a discrete nature. Now, one thing I'll mention now is that the rational numbers are what we call dense in the set of real numbers. That is, given any two numbers, any two real numbers, we can always find an irrational number between them, a rational number between them, but there are still gaps between any two real numbers that are not completely filled by the rational numbers alone, and so we need the irrational numbers to fill those gaps that the rational numbers do not. Okay, so now that we have demonstrated that the set of real numbers is uncountable, we will now show that the set of irrational numbers is uncountable, and we'll do this by contradiction as well. The irrational numbers is uncountable. So first we will suppose that the irrational numbers are countable. Then, as the set of rational numbers is countable, and we know that countable unions of countable sets are countable. We have that the union of the irrational numbers rather, which we are assuming to be countable, with the set of rational numbers is a countable set, as it is a union of two countable sets. But the union of the irrational numbers with the rational numbers gives us the entire set of reals, which by assuming that the irrational numbers is countable leads to the conclusion that the real numbers is countable. But as we have just demonstrated the opposite of this, we have a contradiction. So as, or by contradiction, we have that the irrational numbers as a set is uncountable.